measure two parameters of the black holes. It is the mass, and the second parameter is the spin. And spin of the supermassive black hole is difficult to be measured. And then we will discuss how it can be measured using the Event Horizon Telescope. Okay? And now what is when people say about black hole shadow? So we said that if you look to the orbits, so for example, in the solar system you can have orbits of Mercury, or in the Earth you can have orbits of any rocket, any satellite. At any orbit you will have stable orbit where your satellite will not drop to the Earth. But for the black hole, condition is very different. Because you see, usually physics is very simple. You have equilibrium between centrifugal, centripetal force and then between the gravity. Both of them are in the equilibrium. When you come very close to the black hole, this speed should increase. Speed should increase. When you will come to the innermost stable circular orbit, the speed of the particle becomes equal to the c/2. So it is a very high speed, and then the particle cannot survive. So it can't move faster, and then this orbit becomes unstable, so any deflection interior part will drop it to the black hole. Okay, so then we have innermost stable circular orbit, but when usually it is 6 gamma m over c squared. But if we have photons, photons can come closer. So it is for ordinary star, it can form photon sphere. So each black hole will have photon sphere. It is the innermost stable circular orbit for the massless particle. So now each black hole will have outside event horizon photon sphere. So any particle which will be inside of this photon sphere, it will drop to the black hole. So what we will see? Now we will see that the particles, it is a ray tracing code, so usually particles can come and go to, so there is retrolensing, they can go out, but the particles which will be inside of the photon sphere will drop. So now what people want to see? They want to see photon sphere. So if you would see photon sphere, it is means that there is black hole in the center of this object. And it is very simple. So if you have some bright image, in the bright image there will be a hot spot, dark spot, which you can observe and say it is dark spot which comes from the black hole which eats photons. So it is these are photons eaten by the black hole. So it is similar. For example, in our hotel we have sofa. It is new sofa. In new sofa we have some dirka, some hole, and this hole probably somebody was smoking and made this. Now I know that somebody smoked and made this hole, but this hole is made by the black hole which eats photons. So this something which came from the smoke, it's fabric, but it's photon. So now I want to see how it eats photons, and as soon as I will find this hole, I would say this is from black hole. But now the problem is with the size of this object. So we said that in our galaxy we have let us say 100 billion stars or 200 billion stars in our galaxy, and many of them are black holes. But if we look to the size, so it is, for example, the shadow of the stellar mass black hole, which is 10 solar masses, which is in our galaxy. So it is micro arc seconds. its size 0.001 microarcseconds. So it is small, very small. So it is impossible to observe stellar mass black hole. So it is out of anything. So, and from the whole set of the stars which we have in the space, yes, we have only two objects which are interesting for us. One of them is the Sagittarius A star, which is in the center of the Milky Way, in the center of our galaxy. So it has size about 45 microarcseconds. And then other one, it is in the center of the elliptic galaxy Messier 87. It is about 40 microarcseconds. So from point of view observations, we have only two objects which can be theoretically observed, yes? And then, you see, what is interesting here, we need to observe it, but you see, this, our black hole has mass 4 million solar masses, but it is very close. So, and this M87 is more massive. So this is, you see, it is 1,000 times heavier with compared to supermassive black hole, which is in the center of our galaxy. In spite of this being very far from the distance. So it is, you see, this one is 8 kiloparsecs, yes, but the distance of this, you see, this is much more far, but since it's mass, so I say that in astrophysics, the most important is the mass. So, for example, my mass is 90 kilograms, and I say, as astrophysicist, I would like to be massive. So, as Dima, Dima is also very massive. So, we know that the mass is very important. And you see, for the size of the shadow, mass is very important. Yes? So, M87 has bigger size, and even being far, it may be observed. So, now we have two objects in the space which can be observed, and people started to hunt these objects. So, but the problem is not very simple, and in spite of this, people have observed. So, for the observation, most important is resolution. Yes, resolution is defined by the, for example, you observe in some wavelengths. So there is lambda, yes, lambda, and then it should be divided to d, where d is the size of the your instrument. So why people try to mount 60 meters telescope? Because they want to increase resolution. As bigger your device is, a smaller resolution. So you can observe very tiny objects having a bigger telescope. So for observation of this 40 microarcseconds, you need to have telescope which has the size of the Earth. So then you may say, are you stupid? You say, people are discussing this 20 centimeters telescope, 1 meter telescope, but you say about something this, which is 6,300 kilometers. So you want to have a telescope which has 6,000 kilometers. Then it is the question, and luckily it is possible. So if you have array of radio telescope which is comparable with the size of the Earth, then it is possible. So then D becomes equal to the 6,300 kilometers, yes, and then in the top, what is important? Lambda should be not very big, so with centimeter telescope you can't do it. So you need to go to the sub-millimeter. So it is usually 0.87 millimeter or 1.3 centimeters. There are two wavelengths in which this is operating, and luckily in 2019 the Event Horizon Telescope announced the first image of the supermassive black hole. So, for example, in Russian language, we say, if you don't want to give something to somebody, you say, тебе дырка от бублика. So, we say, bublik, you know, yes, it is donut. There is some cake which has, in the center, it has some hole. So we say it is dyrka от bублика. This cake called bublik, maybe Dima knows the name of the bublik in Czech language. Donut. So for you, in Russian language says, for you, the whole of donut. Okay? So people are not interested in the whole of the donut, but here astronomers are interested in the whole of the donut. So the people are hunting the whole of the donut, and the whole of the donut finally was detected. Okay? This is the whole of the donut, and what is interesting here, so it is a very big object, but the center is comparable with the solar system, and here it is the image, first image of the supermassive black hole. So, and you would say, well, what is interesting here? But I say that it is very beautiful from one side. On other side, you see, it is the image of the accretion disk, and then at the center there is very dim area, it is dark, so it is here supermassive black hole eats all photons, which which eats the photons, and then here you have some bright spots. This part is dark. Then the question is, why this donut in some places is bright, in some places is dark? Yes? So it is the question. So it is meant that the particles in this accretion disk are moving towards the observer in the clockwise direction. And as I said to you in the previous lecture, there is Doppler beaming. So if the particles in the accretion disk are moving with the speed which is close to the speed of the light, they start to radiate in the direction of the motion. It is means that particles in the accretion disk are moving to me, to my direction. Then I see these bright points which are related with now people measured even the direction of the motion of the matter in the accretion disk. We know it, and it is what was expected. So here, what is the problem? The main problem when you have this matter is dense here, and the most radiation is scattered. But luckily, this estimation shows that if we have sub-millimeter, 0.87 millimeter or 1.3 centimeter radiation, it will be transparent. It is the reason why we can observe the whole of donut. So it is why it is interesting. Then you say, okay, you found this whole of donut, yes, and what is interesting with the whole of donut? So the interesting part, the shape of this donut. So in the ideal case, it can be circle, yes, but usually when you cook donut, it will be not circle. So it will be deformed, and then deformation of this hole will give you information about the second parameter, spin. Spin of the black hole can be observed through dent of this donut. So if this donut is not circle, then the black hole is spinning, but then the size of the donut will give you the mass of the black hole. So as bigger size of the hole of the donut, as massive your supermassive black hole. So this form and size, there are two parameters which gives you information about the two parameters of the black hole. So this is very simple, yes. Everything is simple here with compared to this neutron star, so 1000 parameters, we don't care of them. So we have two parameters and, okay. Now this is radio telescope at SUFA, which is under construction. The question was, they promised that it will look in this way. So the question was, how this image will be changed if we will involve this SUFA telescope to the Event Horizon telescope. It seems at the moment, if you look to the Event Horizon telescope, you see here, it is the south pole and to the north pole. So it is the size of the telescope, okay? But somehow this telescope is not good shape, so it should go to the eastern direction. Yes, so in the eastern direction, now if in Africa will come the telescope, then there will be extension in some telescopes here. In the future, when will be this part of the Earth will be involved in this study, then it is in the future it becomes very promising with the resolution. So resolution will be improved, but the problem is because since it is sub-millimeter, so for centimeter it's okay. So you can put centimeter telescope anywhere. The atmosphere is very transparent for the centimeter, but here you should have very good astroclimate. So it is more important, but it becomes more complicated. But anyway, the number of the telescopes which are involved in the Event Horizon telescope will increase with the time, which will improve the sensitivity. But it was about Sagittarius A star, which is in the center. This is Namibian telescope. And this was, if we would assume that black hole is described by the general relativity. But now we don't know, is GR governs physics of the black hole or some other alternative theory of gravity. And then when we look to the, when we look to the shadow, we assume that the shadow is circle-like and then there is some deflection. But when you look to some different stars, it was shown that some quantum black holes can have such shape. Okay, the shadow can have such shape, some dumpy places and something which will have the structure which we assume. So then the question is, for example, this is the shadow of the Kerr black hole with the scalar hair. You see, we assumed this one, but now we get something like this. Yes, it is a shadow which we would observe if the black hole has some hair, some scalar hair, then it can have a very different shape. So it is the shape of the standard black hole will be changed. And then the question is how to describe this. Do we need some new formalism to describe the shape of the shadow of the black hole? So shadow, it is the sharp boundary of the accretion disk. Yes, it is very sharp boundary. And then usually what people do, they look to the radius of the shadow. Yes, this is radius of the shadow. And then there is dent. So on the left-hand side, there is circle, original, and it is the shadow. And then this dent gives you information about parameters of the black hole. So, but as I said that if the shadow is not closed, if it has some different structure, with respect to the circle, then we need to have some formalism which can describe your shadow of any type. So then we look to the we developed one formalism which is called coordinate independent formalism for description of the shadow. And what we assumed. So we assumed that the shadow, it is some curve in the polar coordinates. So it can be any type. And then we expanded this radius of this shadow from some coefficients and Legendre polynomials. And then we look to these coefficients. Okay, so now we say that we don't make any assumption about the boundary of the shadow, and on other hand, we introduce the buried center. So we usually it is difficult to find the center of the shadow, but we developed the buried center of the of this shadow and described it with respect to the buried center, and look to the shadow of the extremely rotating Kerr black hole, where a spin of the black hole cannot exceed 1. Yes? So we say that the spin of the black hole cannot exceed 1 because it is forbidden. So it will destroy the event horizon, then it is impossible. So this cosmic censorship says that extreme it is 0.99, and then we look to the coefficients. C, it is these are coefficients of the expansion, and then what we understood that the first coefficients, 3, 4 coefficients of the expansion are very sufficient to describe the shadow, and then we introduce different deflection parameters, one of them called 1, 2, 3, and we looked how they behave with the time, and when we have how to generate 10 in power 5 times randomly disturbed shadows, and looked how these coefficients are stable with respect. This is the standard Hioki-Maeda deflection, which is introduced by Hioki-Maeda, but these are our parameters, and one of them, delta S3, is very good. So it means that the parameters which are introduced through this expansion in the Legendre polynomials are very good to describe the shape of the shadow if it is very exotic even. Yes, even it is not closed or exotic and so on. And then we wanted to understand. So when we have these expansion parameters, what is the responsibility of each expansion parameter for which parameter of the black hole is it is responsible? And then here you see C0 value is bigger is red, and when it is small it is blue. So now we see that if we have here the different parameters, I think it is the C0. C0 says that it measures, it does not measure, when it is A is equal to 0, it is maximum, so it is responsible for the mass. Yes? And then when we look to the C1, here you can see it is a red, so C1 measures C1, C2, C3 are becoming very important to measure the spin and depending on the inclination angle. You see, inclination angle is also very important. Yes, for example, for measurement of the mass, inclination angle is not very important, but when we have spinning black hole, inclination plays very important role. So inclination angle is, and here you can see the, okay, I will not discuss these constraints. This is very important. So now what we say, so for, as I said in the previous lecture, now it is important how other astrophysical objects can mimic Kerr black hole. Okay? Now there is, from one side we say that it is interesting to study alternative or modified gravity theories, but even without general relativity, there are exotic objects. There is exact analytical solution of the Einstein equations, of vacuum Einstein equations, which is called gamma metric. So, according to Birchhoff's theorem, your black hole cannot be deformed. Yes, so it is idealistic. But here you can get the space-time which has deformation. So it is deformed, but it is the exact analytical solution of the. So it is not black hole then. So it has some surface with infinite redshift, and it is called, this object called gamma metric. Okay, this gamma metric, it is some deformed gravitational objects, and then we may look, as I said, we measure two parameters in the, for example, for the Sagittarius A star. So it is the radius. And then we see how is this radius depends on the, depending on the inclination angle here, you see? This is inclination angle, and here it is the parameter gamma. So parameter gamma, so now you can see, depending on the inclination angle and depending on the gamma parameter, the size of the black hole depends on the inclination angle and plus on the deformation parameter, which is responsible for the deformation, and comparison of the shadow results. For example, with the, here it is measured, so between 5.2 to something, and then you can see, so if it is inclination angle is 0, so you can get constraint to the parameter of the gamma. So parameter of the gamma can be between 0.5 and 0.7, let us say, yes? So the size, the measured size of the Sagittarius A star can give you constraint to the parameters of the deformation. So if it is described by the gamma factor, then gamma should change in this range. So now you can produce some numerical images for the gamma in the gamma space-time with the inclination 17 degrees. And here you can see how the shape here in the first line, this is gamma 0.5, gamma changes, and you see how this accretion disk and shadow changes. Here, this is the size of the shadow, and this is also size of the shadow. So the size of the shadow depends on the gamma parameter. Yes, gamma parameter is responsible. So this we can observe from the numerical modeling. It is now you saw the film Interstellar, yes? In the Interstellar, why we see this head-like the structure? Because it is related to the retrolensing. So what is the retrolensing? So sitting here, I can see my backside. So black hole is very interesting object. It can see the backside because the light go back and come on other direction. Then its image becomes this head-like. This you can see how its image depends on for the inclination angle 80, it is the image of the accretion disk. And why we trust to these results? Because we have two students, one of them Song Lee from Shanghai, and the other one is Timurbek Mirzaev. Both of them are working in the different simulations. They use different programs, and then we compare how the images which are produced by Timurbek and Song Lee coincide each other, and if they don't coincide, we do again calculations, and now we got this agreement because both calculations should coincide. And here you can see it is a Schwarzschild space-time, and this one is when gamma is equal to 0.5. So you see the size of the shadow depends on the gamma factor. And these are calculations for the accretion disk which are made by, let us say, by Bardiev Dilshot. So he's using our cluster and doing some calculations. And now what we can do, we can look to the energetics. So as I said in the previous part, so energetics of the black holes is very important. Okay? So since it is very heavy, for example, some black holes have 10 billion solar masses. Okay? 10 billion solar masses. So it means that the energy of this object is 10 billions is bigger with compared to energy of the sun. So you say that sun is very bright. So when you go outside in summer, you suffer from its heating, yes? But this object has 10 billion times bigger energy, yes, from one side. On other hand, we said that the efficiency of the sun is 0.1%, but efficiency of the accretion is 10%. Then it is 100 times more efficient. So from one side it has 10 billion times more energy, and on other hand it is 100 times more efficient than sun. Then it's so now you can understand how energetic these black holes, and this can be confirmed from the activity of active galactic nuclei. So active galactic nuclei are expected as supermassive black holes which spend their energy, and the first model for this explanation of their energy was suggested by Penrose. Roger Penrose in 1969 suggested the mechanism which was called Penrose mechanism. So assumption was if some particles comes to the ergosphere, it is decays to the two particles, and one particle lives with the bigger energy and it extracts the energy. Okay? Then the question, people were not very interested to these mechanisms. Why? Because when they started to calculate the cross-section of this reaction, cross-section of this reaction was equal to almost zero. So it is very beautiful idea, but the cross-section is very low. So it is not applicable to the astrophysical cases. And then this Blandford-Znaeck mechanism in 1977 came. So they said that it is the unipolar induction is responsible for the energy extraction. So you have magnetic field and rotating object, and then this unipolar inductor is the source of the energy which is coming. So this rotation of the kinetic energy of the black hole is transformed to electromagnetic energy through magnetic field which exists there. So then it is called Blandford-Znaeck effect, and Naresh Dadic with his collaborators, he suggested magnetic Penrose effect. So he asked the question, what will be happened if magnetic field played plays a role of catalyst. Would it improve the cross-section of the reaction? And the answer was positive. So then we started to be interested to the efficiency of the magnetic Penrose process for the different black hole spins. So, but what is important here in the magnetic Penrose process, Martin knows, the most important here, we say that when we look to the cosmic rays, yes? In the cosmic rays, we have this shower of the particles, which are coming from the particles which we called, oh my God, yes? So they had very huge energy, and these particles started to be called as oh my God. And the question is, from where these oh my God particles are coming? And now we know the exact answer. These oh my God particles are coming from the supermassive black holes. So supermassive black holes are the source of these oh my God particles, and it is means that there should be some mechanisms which will accelerate the protons in the ergosphere of these black holes. And here this we call this high mechanism. So it is usually for neutral particles. So the black hole is slightly charged because it is volt charge, it is rotating, and then when we have a proton, so the neutral particle is, I think there is some, so neutral particle will be decay to proton and something, it is beta decay, yes, and in the proton will be accelerated by the charge of the supermassive black hole, and then it is called magnetic Penrose effect, and then we can calculate the energy. So energy which is produced from the black hole strongly depends on their mass. So for example, we said that in the center of our galaxy we have mass about 4 million solar masses. So here in the center of our galaxy, our black hole is only 4 million masses, only. But in the center of the Messier 87, it is 6 billion solar masses, okay? You see the difference. And then depending on the mass, so this energy, for example, here on the axis, this is the horizontal axis shows the ambient magnetic field in Gauss. So usually for the supermassive black hole, this magnetic field is estimated up to 10,000 Gauss. So 10 in power 4 Gauss. So it is the maximum number. Now you can see this is spin of the black hole. So it is very reasonable, 0.8 solar masses. Then we see that if we have magnetic field about 10 in power 4 Gauss, yes, and then mass of the central object is 10 billion solar masses, then the energy of the particle 10 in power 21 electron volt, which we call oh my God particle, can be created there. So magnetic Penrose process can be responsible for the energy which is produced in the center of the galaxies. And here you can see, for example, Sagittarius A star can produce maximum energy of the particles is 10 in power 15 electron volts. But here you can see these objects M87 also does not have such masses, but there are some objects which is called NGC 1052 or which can produce the particles which are above 10 in power 20 electron volts, which are called oh my God particles. And this what we claim with Martin, yes, Martin, do we claim this? So we say that what? Yeah, but anyway, this is what we. So Arman says that if there are experiments which shows that these oh my God particles are produced in the center of the by blazars in the center of the galaxies by supermassive black holes. So ice cube experiment says that these particles are produced there, and Arman says it is due to the magnetic Penrose process. So everything is reasonable. So you have very heavy massive black hole, you have some reasonable magnetic field, and then this highly spinning black hole, then it gives you, so then this is, there were some papers about the measurement of the magnetic field, yes? So there are different measurements, and which says that the presence of the magnetic field in the black hole environment, supermassive black hole. One of them is the polarization of the M87. So initially this donut was measured, image of the donut, and then as the next step there was measured polarization. The polarization of the light comes from the presence of the magnetic field, and this polarization shows that there is test weak magnetic field in the environment of M87, so it is very good. So it is compatible with what Arman says, yes. And then there were, we were interesting how if the black hole is rotating and in addition it moves, can it create the energy loss? So it is meant, we show that it can be reasonable radiation which can come from the motion if it is boosted. And other thing which is very interesting, which in which Bobber is interested. So when you look to the collision of the two black holes, here you see it is the time, yes. Here we have the merger, and it is the total signal. The total signal, for example, when we have black hole collision merger, the gravitational wave signal is less than 1 second. For example, for the first merger of the two black holes, it was 0.43 seconds. So it was less than 1 second. But even having less than 1 second, we have 3 independent regimes. One of them called in spiral. So in spiral, when these two black holes are rotating with respect to the one center, and what do you think? When two black holes collide each other, what is the speed of the black hole? Colliding black hole. What is the speed of the colliding black hole? What do you think? So it is almost equal to the speed of the light. Can you imagine the macroscopic object having 30 solar masses and moving with the speed of the light? So when you look to the Mercedes, and when two Mercedes collide each other, moving with the speed of the 200 kilometers per second, which is very, very low, you say that it is a catastrophe. But here you have 30 solar masses, moving with the speed of the light, and they collide each other. Is it catastrophe? Yes, it is catastrophe. Yes, and then in this catastrophe we have this in spiral regime. So here analytics approach works, because you see what is the main problem of the general relativity with respect to the classical electrodynamics. In the classical electrodynamics, if you have two body problem, so you have one electric charge, second electric charge, you can find the solution of the each electric charge separately, and then you can simply combine them and say, okay, I use the symmetry and find solution of one charge, and then find solution of the second charge, and then the simple combination gives me the total electric field. Yes, but here it does not work. It is since the gravitational field is highly nonlinear, so even for two-body problem, you need to solve it numerically. So this part, for example, after merger, so we have this something which cannot be solved without. So here we have template with numerical relativity, but then for this we should have very powerful supercomputers to study this part. But and then there is the last part. So when we have, you see, this signal is very short, but it has very different stages, and this is the last stage called ring down. In ring down, what I said, that nature wants a black hole to be very ideal, so it should be highly idealistic. So even it does not have this event horizon, hypothetical event horizon should be very idealistic. The nature does not want its deflection even for nanometer. So then what it makes the nature, the extra part of the matter is going to the space, and this extra part is equal to, for example, for the two objects with 30-30, it was equal to 3 solar masses. Can you imagine 3 solar masses radiated in the period which is less than 1 second? So then if you compare with the energy which is produced through this event, if you say that in our galaxy we have 100 billion galaxies, each has 200 billion stars, and each of them radiate energy. So if you compare the energy which is released from the whole universe at one stage, if it will be comparable, this energy will be even bigger. So can you imagine one very small event? So it is very catastrophic event, and then this ring down frequency. So these oscillations will dump with the time. So now what is interesting? It is a measurement of the damping time of this measurement, how these perturbations are damped, so decayed with the time, and what are their frequencies. Their frequencies should be around 300 hertz, because it is they do 300 revolutions per second before, and this was our interest. So we were looking to the how this different scalar electromagnetic and gravitational radiations this decay. So for example, when we calculate the frequencies, it has imaginary and then real part. Real part is the frequency, and we compare with the Schwarz. What was interesting here? You see? What on the left-hand side we have the regular black hole. So it is a black hole where GR coupled to nonlinear electrodynamics is the source of the gravity. We have matter plus nonlinear electrodynamic source, and then we looked how these perturbations, for example, behave with the time, especially electromagnetic perturbations. Here, this one is for Reissner-Nordström, for the Reissner-Nordström type black hole. So the electromagnetic perturbation will decay with the time. So they rapidly decay, even faster with compared to other perturbations. But here, if we have regular black hole, then electromagnetic perturbation will survive for very long time. So it is soliton-like solution for the electromagnetic perturbations if our black hole is regular. So for regular black hole, we have such solution. So it is mean. So if we would find some now we don't see any electromagnetic counterparts, but if we would observe electromagnetic perturbations which will survive for a long time, it would mean that that black hole is a regular one. So there is some hint, some distinguishing of them. So this is what I wanted to discuss about black holes. I think the other part is related with the pulsars and magnetars, and Jaulon discussed many issues which were related to them. Yes? So we can discuss some part of them, because I would say that supernova explosions, yes? So you see what we see before observation of the telescope, we saw only 5 supernova explosions up to Galileo Galilei. There were only 5. This is supernova which is very famous. It is supernova 1054, which is called Crab Nebula. And then these are very bright events which can happen in the nature. So this is beautiful picture comes from the, this one is supernova 1006, so which was observed by Ibn Sina. So it is, maybe you can read. Previously we used this script, but now we use Cyrillic and Latin. So, and then in 1006, one of them was observed by Ibn Sina in Bukhara, in Central Asia. So this is the indicator. And here you can see the supernova 2017 in the galaxy NGC 3938, which was observed at the Majdanek Observatory. So Majdanek Observatory is the observatory of our institute. And here you can see this is explosion 2017 EIN. So this is 1 second resolution. So it is it has very good resolution actually. Okay, so then this object was observed, and then our task, we have Morozova Victoria, now he is in the Pennsylvania State University. She developed this SNEC, supernova explosion program. And what we looked, so this is data which were obtained during the days in the R filter and B filter, and this one is the bolometric. So we calculated bolometric luminosity using this data from the filters obtained during the, let us say, 60 or 70 days. And then we look to the different phase. This is the observational data, and this yellow